Um, all right, so let's get started. So what we talked about last time is if we have a function f of x, y, z, just to kind of recap, if f of x, y, z equals 0, and we have a point at some point p0 is x0, y0, z0. We decided that the equation of the tangent plane at p0 was f sub x, x minus x0, plus f sub y, y minus y0, plus f sub z, z minus z0.
I have a question. Is there like a little symbol or something that stands for the equation of the tangent plane?
There's not.
It was really bothering me that I couldn't make it equal.
So you couldn't make it
So
equal.
I couldn't like write a little symbol and say
Equals
and
equal.
the
No,
equation.
so there's not a special symbol for the equation of a tangent plane.
Okay.
So that would be nice, because it'd be nice to, yeah, to condense that.
Let's make a symbol.
Make a symbol.
Yeah, and then we'll always know when we'll use it. Like a square instead of the little upside down triangle. Let's just use square.
It's like a diamond.
Oh, I like the diamond
Not
idea.
sideways square.
Let's do sideways square. Okay?
All right, so we need to patent our idea at the math patent office.
No,
Well, if I
let's do
put
it
that,
first class.
if I put that on a quiz, you're gonna know what it means. Who's talked about this?
Yeah.
Okay,
Okay, cool.
I can deal with that.
Equation of tangent.
Um,
There, I got it.
all right.
Nice. That's how
So
it's going.
this is the equation of our tangent plane at the point p0. So, and our direction numbers for our tangent plane are given by the gradient of f. So the gradient of f gives us a normal vector. That was our big idea, one of our big ideas from the last unit. So another type of problem that we can do now that we have this idea of tangent, the gradient being our tangent vectors, is we can find the equation of the tangent line to the intersection of two surfaces. So let's look at how we do that. This is my second type of problem that I like from this unit. So we have two surfaces that we can write the equation that gives us our surface x squared plus y squared equals z, and z equals 4 minus y. And the problem that we're trying to solve is we want symmetric equations for the line, for the tangent line to the curve of intersection. So we have these two surfaces, and they're going to intersect in some curve, and we want to find the tangent line to the curve of intersection at point 2, negative 1, 5. So these curves are going to intersect somewhere. The intersection is, or the surfaces are going to intersect somewhere. The intersection is going to be a curve. We want to write the equation, the symmetric equations for the tangent line to the curve at 2, negative 1, 5. So the way I'm going to go about this is I'm going to write for this first equation, I'm going to say that f of x, y, z equals x squared plus y squared minus z. And I'm going to say that g of x, y, z equals 4 minus y minus z. So these are my functions of 3 variables. Anybody have an idea of how we're going to proceed? How we're going to proceed to solve this problem? Find the gradient. So we're going to find the gradient of each surface. That's going to give us a normal vector to each surface. And then what do we do?
Dot product. Normal tangent line.
Normal tangent line. So we have a normal vector to each surface at this point. So if I say let's say this is just a quick sketch. There's the curve of intersection. There's a normal vector. This is going to be del G, and this is going to be del F, and we want a vector in the direction of this tangent line. So I'm going to call that my vector tangent. Any ideas? If we add them, we're going to get a vector that goes off in. Not necessarily. There we go. Cross product.
Yeah.
If we find the normal vector to the surface, to each surface at the point, the cross product is going to point in the direction of the line of intersection, to the tangent line of intersection. So we're going to find the gradient of each of the surfaces at the point. We're going to take the cross product. Our cross product is going to give us the direction of the tangent line, and then we can use that to write our equation, our symmetric equations for the tangent line. So del F, which gives us our first normal vector. Del F is going to be 2x I plus 2y j minus k. And del G is minus j minus k. So these are our normal vectors to our surfaces, and we're interested in this particular point where that's on this curve of intersection. So del F at our point is going to be 4i minus 2j minus k. Let's see, two.
Oh, no, right there.
All right. And del G at our point is just going to be minus j minus k. So I take the cross product. The cross product is going to point in the direction of the tangent line. So I'm going to switch pages to do the cross product. Or I can do it here. I'm not going to write the whole thing out. We know how to take cross products. So del F cross del G gives me I plus 4j plus 4k. This is in the direction. Del F cross del G is in the direction of the tangent line. So this gives us the direction numbers for the vector that's parallel to the line that we're interested in. The cross product gives us our direction numbers. So I'm going to switch pages. So our direction numbers for the line are A equals 1, B equals 4, and C equals 4. So our symmetric equations for the line, for the tangent line to the curve of intersection at our point are going to be x minus 2 over 1 equals y plus 1 over 4 equals z minus 5 over 4. So those are our equations of our tangent line. If we wanted to write the parametric equations, how would we write the parametric equations? Right, so everything equals t, our parameter is t. So we could write x equals 2 plus t, y equals -1 plus 4t, and z equals (5 plus 4t). So those would be our parametric equations for the line. So if the problem asks us for our parametric equations, we could write it like this. These are the symmetric equations. Questions on that particular type of problem? That's again another kind of problem that I like. I like the way it puts together lots of different things that we've been talking about. All right, the last topic that we need to talk about for this section is angle of inclination. So we've been talking about these tangent planes, and we're interested in angle of inclination. We're interested in the angle that our tangent plane makes with the xy plane. So we're going to define the angle of inclination as an angle, and we want it to be between 0 and 2 pi, or 0 and pi over 2. So theta is 0 is less than or equal to theta less than or equal to pi over 2. So this is the angle that the plane makes with the xy plane. So if we have two planes, how do we figure out the angle between the two planes? Thinking back to chapter 11. So we define the angle between two planes as the angle between their normal vectors. So we want, what we're looking for when we're looking for the angle between two planes is the angle between the normal vectors. She's not allowed to leave. So our angle of inclination is the angle between the normal vectors. The normal vector to the xy plane is what? The z-axis. And if we represent that as a vector? Okay. So we want the angle between our normal vector to our plane and k hat. So we're looking for the angle between our plane and k hat. How do we find the angle between two planes? It has to do with the dot product. So the angle between, we find our angle of inclination with the dot product. So we remember that we said that the angle between two planes, the angle between two vectors, we could say that the cosine of the angle is A dot B over the length of A times the length of B. So we're interested in the angle between our normal vector and the z-axis, or k hat. So our angle of inclination is going to be given by the cosine of the angle, and we're going to do absolute value because we want our angle to be between 0 and pi over 2. The absolute value of n dot k hat over the length of n, and I'm going to write k hat even though k hat, the length of k hat is 1. So just the absolute value of n dot k hat over the length of n. And the absolute value makes sure that our angle is between 0 and pi over 2. That gives us our angle of inclination. Why do you think we would be interested Why do you think we'd be interested in the angle of inclination? So think back to what we did with, we've been talking about derivatives. This whole chapter is about derivatives. So Emily says it has something to do, or it's related to slope. So if the angle of inclination is 0, if our tangent plane is parallel to the xy plane, what does that tell us about the tangent plane? It's horizontal. What do you think happens when the tangent plane is horizontal? The derivatives are 0, so if we're thinking of our surface, it's flat. So what happens in single variable calculus? What happens when the tangent line is horizontal? Maximum or minimum? When the tangent plane is horizontal, our surface is at a maximum or minimum. So that's why we would be interested in angle of inclination. Angle of inclination tells us something about how our surface, how our function is behaving.
Can't we just find that with the derivative function without maximum or minimum? Why do we have to go into the angle of inclination?
It's just another way of looking at it. Just like in single variable calculus where they would give you a problem and they said the tangent line is such and such, and so it's just a way to work from a different direction.
Also, like solving the derivative for 0.
Solving for the derivative equals 0, you end up having to do simultaneous equations because we're talking about a multivariable function. It can be complicated. This might give a different way of looking at it. All right, let's do a couple of examples using our angle of inclination, and then we'll be done for today. So we have a surface. Our surface given by 2xy minus z squared, minus z cubed. This is our surface. We want the angle of inclination. Angle of inclination at the point 222. So our function, our 3-variable function, f of x, y, z, is 2xy minus z cubed. We want our normal vector. We want a normal vector. Our gradient gives us our normal vector, so del f is 2yi plus 2xj minus 3z squared k. And at our point 222, the point that we're interested in, our gradient is going to be 4i plus 4j minus 12k. And this gives us our normal vector. So n, our normal vector to our surface at that point, is 4i plus 4j minus 12k. That's our normal vector. Our cosine of our angle of inclination is going to be the dot product of n dot k, the absolute value, over the length of n. So we need to calculate our dot product and our length. N dot k absolute value is just 12. So we're only interested in the k component. And the length of n, if I calculate that out, I end up with 4 square root 11. So my angle, cosine of my angle, is just 12 over 4 square root of 11. So that gives me that my angle theta is approximately 25.24 degrees. So the angle of inclination of that plane is approximately 25.24 degrees. Questions on that? All right, let me do one more example talking about the horizontal tangent plane. Let's say we have z equals 3x squared plus 2y squared minus 3x plus 4y minus 5. We want to know where the tangent plane is horizontal.
Do the symbol for that. Where the
Oh, our symbol?
diamond of F is horizontal.
So we're going to, are we doing it this way?
Yeah.
Yeah,
Like that?
yeah,
That's our tangent plane?
yeah.
Okay. I'll put this in quotes. So we want where what are we going to call this symbol now?
Diamond F.
Diamond F. Diamond F. Where's Diamond F? It reminds me of David Lee Roth and Van Halen. His nickname was Diamond Dave. That's the first thing I thought. Diamond Dave. Where's Diamond F? Where's Diamond F horizontal? All right. So how are we going to, given this information, how are we going to figure out where the tangent plane is horizontal? How are we going to figure that out?
When the inclination is 0.
When the angle of inclination is 0?
Yes.
Okay, that's one way we could do it. When the angle of inclination is 0, how are the normal vector and the z-axis related?
Parallel.
They're parallel.
Yeah.
If the normal vector is parallel to the z-axis, what are the x and y components of the normal vector? 0. So we can find our normal vector. Our normal vector is going to be a function of x and y. We can set the x component to 0, y component to 0, and we'll have simultaneous equations. And we solve those simultaneous equations to figure out when they're both 0. And that'll tell us when the normal vector is parallel to the z-axis. Going straight to the angle of inclination, the angle of inclination, because we have a function here, it's going to be a function of x and y. And to find where that equals 0, where we have the cosine of an angle, some function of x and y, could be tricky. So we're going to solve simultaneous equations.
Isn't that just like the same thing as what we could have done before the angle of inclination?
What's that?
Isn't that like if we didn't have the angle of inclination, we would just like take the derivative in respect to x and then derivative in respect to y, so equal to each other equals 0?
Yes,
And that's like what we're going to do right here.
that's what we're doing right here.
Yeah.
Right. That's what we're doing here. So this is related to the angle of inclination, but we're going about it a different way. We're talking about its relationship to the normal vector to the z axis. So it has to do with the angle of inclination, but we're not necessarily using the angle of inclination to solve this problem. All right. So let's find our normal vector. So del f is the normal vector. So we need to write our function. We're going to write f of x, y, z. We need our function of 3 variables. I'm going to write that as 3x squared plus 2y squared minus 3x plus 4y minus z minus 5. So I'm just subtracting z from both sides. Del f, my normal vector, is going to be, when I calculate this out, is 6x minus 3 I plus 4y plus 4 j minus k. And we need to know when our normal vector is parallel to the z-axis, the x component and the y component are both 0. So we're looking at 6x minus 3 equals 0 and 4y minus 4 equals 0. In this particular problem, it works out really nicely. We don't have a complicated set of simultaneous equations to solve. So x equals 1/2. Y equals -1.
No, it equals 1.
Is it positive 1? Let's see. Y is 1.
It should be +4.
This should be +4. Thank you. So y is -1. I can plug x and y, these x's and y's in here to get z. This gives me z equals -31/4. So at our point 1/2, -1, -31/4, our tangent plane is horizontal. Oh, diamond F. So this point would also be a point of relative maximum or minimum, where our tangent plane is horizontal. And we'll talk, that's our next topic that we're going to talk about, is analyzing multivariable functions for maximums and minimums. Any questions? All right. Homework. All right, there you go.
It's next
It's nice?